everybody.
Okay. Thank you. So speaking of coffee, I hope you have had your espresso shots already. Anybody watching on YouTube can play it back at half speed. First, a little disclaimer. I'm going to be talking about concurrency and what should you do in your production applications, so servers and stuff. Like performance considerations, I don't care about them in this talk that much. And of course, you might write more code to make it production ready. And of course, I'll skip plenty of exceptions because that's boring. Yeah. Also, if you can't read the slides fast enough or the code, then don't worry about it. You can read them later. OK. The rough outline, each topic gets a little bit more difficult. First is the rules of thumb, like what you should do, and then we go into like how you can, or the main things about the standard concurrency primitives we have in Go. And finally, how to build your own primitives, which is probably the more interesting part here. But rules of thumbs are usually really nice to get started with. These are the mistakes I guess beginners make and experience alike. So yeah, let's get started. The main thing about concurrency is don't. There's so many ways it can go wrong, and I've literally seen this code in someone's code base. So you don't need to use concurrency. It probably doesn't make your production application faster unless it's in a certain specific scenario. You're handling concurrent requests anyways. And of course, code without concurrency is easier to understand. So yeah, avoid it if you can. Similarly, when you're designing your APIs, just write the synchronous version. You can have the helping concurrent version there if you want to, but the main thing is it's much easier to turn a synchronous API to a concurrent one. Yeah. And of course, like the concurrent API, as you can see, looks much worse as well, like much harder to use correctly. There are two really nice features in Go that help you avoid data races. One is tparallel and dash race. The tparallel makes your tests go in parallel. Yeah. This means that any shared state in your code base will show up somehow. And of course, race detector finds your data races, which is one of the best features, I think, in Go. And speaking of global variables, don't have them. I'm sure you have at least one of them, but yeah, they do mess up your concurrent code. And if you're writing concurrent tests, then all the tests hit the concurrent or the shared state and will mess up your tests as well. For example, this is one of the most common things. You have a logger, the standard log, somewhere in the depths of your code base. And when you run two tests in parallel, you can see that the alpha and beta, like the output in the code test verbose log, are out of order, right? This is because you're not using the right logger, which should be passed down somehow to your, the lowest levels where you use it. This is also a really common thing that people mess up, is that you should never leave a Go routine just running around somewhere. You always should wait them. It's not like about, how to say, ensuring that, oh yeah, I need to wait for them to finish. It's about ensuring that they do finish. If your Go routine gets stuck in a deadlock or like an infinite loop, then your tests will detect them if you have waited for all of the Go routines in your code base. Of course, there are certain scenarios where you're kind of doing some context cancellation propagation where it's fine. So yeah, just wait for them in some way. Speaking of context, your code should be aware of context cancellations. For example, here the time sleep, it doesn't care about what the user wanted. Like, did they want to time out the call or not? Like, on the other side, you get this version where it does properly wait for the context cancellation and kind of ensure that when the user presses Control-C, it stops as soon as possible. So if you're not aware of context cancellation, there's like a context.done channel that is terminated when the context is canceled, or there's context.error, which you can check that has the user canceled the operation. If the operation takes, let's say, more than 50 milliseconds, you should have somewhere like context error handling. Even here, the OS read file isn't ideal because it will block until you've read the whole file. So you need to kind of pass the context into the reading of file until it's finished reading. So if you're coming from another language, one common thing to do is create worker pools. There's no need for it in Go, usually. It will make your stack traces harder to read. It will use more resources when they are on standby, and they are often slower than just spawning a coroutine. So there are one way to avoid worker pools. Worker pools is to create a limiter which prevents from too many coroutines to be started at the same time, which achieves kind of similar needs as a worker pool. Avoid polling state, right? It's really easy to kind of create state transitions with just polling and seeing what has changed. However, that means that your coroutine that's doing the polling is always running. It's wasting resources, and it's not reacting fast enough to the incoming signals. In this case, it's possible to replace it with a channel where you send messages. There are other ways to avoid polling the state, except in some scenarios where you're like calling an external API and you have no control over it, what they do. Defer post actions. It's quite common that people start with the code on the left, then they add an if statement into the code base and forget to unlock the mutex. So this, of course, is kind of discoverable easily. However, you still waste a lot of time debugging this concurrent code and figuring out where things go wrong. Don't expose your private things, I guess. The more places you use your logs, or the wider the scope, the more likely you are to mess them up. So narrow the scope of your logs as much as possible and try to kind of limit them to a really small space. Right? If your concurrent code doesn't fit into your head, it probably has a bug in it. Yeah, and finally, name your coroutines. Treat them like children, I guess. So if you have names to all of your coroutines, any stack trace that you get will look nicer, and you can understand what's running and what's not. Even so, if you use the golang debugger, it also shows you the names of the coroutines, which means you can much easily find the coroutine that you are looking for. So we got through the rules of thumb. Yeah. I know this is a lot. You can go over the slides later, but these are, I think, one of the best ways to prevent concurrent issues in your code base in the first place. So production ready means that the code is maintainable and you can change it without worrying about breaking it in some sense, right? There are, of course, many different bugs that can happen in concurrent code that I didn't cover. However, there's probably not an easy single solution for them. Yeah. So let's get to the fun part, I guess. Quiz time. So this will be a flash quiz. Like, imagine that you are reviewing someone's code, and your task is to spot the mistake so you can go on with your life to coding, I guess. Yeah. So, are you ready? Yeah? Yeah? OK. So, spot the 2 bugs here. I think I'm in the way. OK. So, there are 2 important bugs here that you should be trained to detect. One is this database. Because the coroutine is started in the background, it means that there's no synchronization between the database closing at some point in the future, which means that this coroutine might call this method on a closed database, right? And it mainly affects your tests, like some flaky failure, and you're kind of then wondering why is the database closed in here, but yeah, it happens in the background. The other thing is our context. This context comes from the user, which means that the user might cancel this asynchronous operation. You don't want that. If it's a background operation, you probably want it to be scoped to the life of using the program context, like the root context, or something else, not the user itself. You might still want to add some timeouts here, but yeah, you should be aware which context you are using and who's going to cancel it. OK? Next one. This is probably slightly easier because many people have hit it. The issue here is this. The wait and the add are in separate coroutines, which means that one of them can be executed first or before one and the other, right? So if you get the wait, you hit the wait, and you then hit the add, it means that the code above doesn't actually wait for the coroutines. Like, so you get this problem. Common mistake number 4. So this is the example about later code modifications breaking your code. Like, somebody probably added this file path check in there at a later date, and it doesn't account for that, oh, the method wants, or the function process concurrently wants to wait for all the items, not, and it kind of ignores the skipped things. So you will get a deadlock, right? Number 5. This is slightly less obvious. You need to imagine what the evict old items does. So the non-obvious part here is that we are not handling the context cancellation, which means that, let's say there's 10,000 user requests, comes into the cache, and let's say half of them get cancelled. Then they still need to wait for the mutex to be unlocked before they can exit this function or method. And of course, we don't know how much time is evict all items takes. Maybe it's O1 operation and it doesn't matter. Maybe it's ON and it does matter. So if you're using mutexes, it means that you should use them only for a short period of time, right? Something that takes really, let's say, an assignment or kind of appending to a slice at most, right? If you're doing more than that, then it's very likely that you can hit these scenarios. And of course, you might be thinking, oh, I'll use an RW mutex. Then you start hitting other problems with regards to contention on the mutex itself in certain scenarios. So you should kind of be aware the trade-offs of your tools. Sorry about the slanted text, it didn't fit. Next puzzle or problem. Okay. Here, the problem is we didn't close the channel, right? Like, it's really easy to miss if it's not deferred in the first place. If you're trained to look at the defer of close, then it's much easier to know that, oh, it's not deferred, probably it leaks somewhere, right? So all in all, it means that I usually avoid these things in my domain code, right? They have tremendous flexibility. However, that also means that they don't use the clear semantics that they want them to have. They are more difficult to review, and yeah, there are many ways to break them, right? Of course, like, it's not the end of the world if you do use them. It just takes twice or 3 times more to review that code. I should mention that select is not mentioned here, right? Because select kind of converges things, and it doesn't kind of, for some reason, I haven't encountered too many problems with selects in code bases. So yeah, seems fine to me. So here's how I choose my what to use as my concurrency primitive. First, I'll really think whether do I need the concurrency there? Can I avoid it? Like, my life is going to be much easier if I avoid it. Then I will look into error group, which can start multiple coroutines. Konrad already mentioned it in his talk. Sync once is also pretty nice. There are many nicer kind of synchronization utilities in the x/sync package. And then I will consider a custom solution before going further down the line here. And of course, as I mentioned, the sync mutex in certain scenarios is completely fine. It's not going to add problems to your code base. When you're implementing custom primitives, there are many things you can use. They are completely fine in that context because your scope is going to be smaller. So error group, it's probably going to be your most useful thing. I'm not going to go over the documentation of it. And you might be wondering, like, what do I do if I cannot find my own or find my synchronization primitive? So let's build your own artisanal concurrency primitives. You might be thinking, I'm not smart enough to build a concurrency primitive. The point is that an ad hoc concurrency primitive in your domain code is much harder to get right than a separate concurrency primitive that you built with properly testing and stuff, right? So, yeah. And of course, I just show some examples because you need to figure out what works for you. These are examples. You can derive your own ideas. OK, let's take the, more code, of course. Sleeping. We saw the first example of you should not use sleep. Here's how you can replace it. We create a simple function that handles the context properly, stops the timer, and handles things nicely. And you can easily use it. So nothing complicated, right? So you should be able to write this. Next thing, let's assume you are writing tests and we want to test things concurrently. So we'll write a simple wrapper that does this synchronization and waiting properly for us and ensures that we don't kind of leak these things. And when you write a test, you can write it like this. So you don't have this deferred wait somewhere in your code base, and you are more likely to get right this function call than other things. Right? Of course, there are variations. Like, what should happen if one fails? Should we add context into this function? Well, figure it out. There is a popular alternative to sync mutex that can handle context cancellation. You can use a channel with a single element. And you can then use it to store the state of your thing that you're protecting. So first, we'll check whether the context has been cancelled, because we don't want to wonder whether the select picks one or the other, right? And then the usage is like this, right? We talked about the limiter, like the semaphore of channel that you can prevent too many coroutines to start. Let's say we want to write an API that looks like this. We'll check whether the limiter can start something, or like it blocks until it's started. If the context is cancelled, the started will return false. So how you implement it? We have like the limiting semaphore or the channel. We check first whether the context is cancelled. Then we ensure that we are using the semaphore correctly. And eventually, we kind of add it to the work group and kind of handle the finishing of it. And that's it. And you wait for it when you need it. So that's a limiter. Concurrent processing of a slice. Here I'll show a different way of defining your arguments to the concurrency primitive. Instead of passing them as an argument, you can create a struct that has a method. It makes a nice way to reuse your parameters. The code isn't too much different from the concurrently code base. It mainly kind of uses the limiter, and we'll figure out the bounds of our kind of processing and then start them. And the code then will look something like this. Of course, this example will probably run slower than the sequential version, so not useful in this case. Async processes in server. So this is the case where I showed where the server started a background coroutine. How would we handle this? Let's say we implement it like this. The first thing we need to is to hook up our root context to the thing that manages the background coroutines. So we create some struct that holds them. And of course, we need to start it before we start serving HTTP requests. Otherwise, the coroutine manager isn't ready. And then we can use it, let's say, the same way as our limiter. Right? And of course, here we need to pass the correct context around, because the server and the server and the user context are different, and we need to be able to distinguish between them. So how does it look like? We have a root context there, and the main logic is here. We'll check whether either of these contexts are cancelled. Is the server shutting down? Did the user cancel the operation? Then we'll wait for any of those to happen, whether we can start the coroutine or anybody else canceled it. And finally, we do the usual dance of starting a coroutine with the error group. There's the fence. You can read this later. I guess we'll skip over it due to time, because that was a lot. I did manage to get the blog post up. You can read over there. Brian Mills has like a really nice talk about condition variables and different issues there. And there is real-world concurrency bugs that is a nice article. And if you want to go into deeper, there's an instructional book on semaphores. Thank you.